All right, everyone. This is going to be the first little video lecture I'm going to be posting. I think we finished off last time on 2.1 before we had left, talking about functions, when things are functions. And I gave you all a list of all that. Now we're going to go on to 2.2. We talked a little bit about what we're going to be doing in 2.2 before we left. So let's go ahead and start from the beginning, right? We're going to be talking about when functions are increasing and decreasing, when functions are constant, identify like relative maxes and mins of these functions, right? Some stuff that it's kind of high points and low points, not necessarily the largest and smallest value. We're also going to be identifying when functions are even and odd and how we can recognize even functions, odd functions, things that are neither even nor odd, and the symmetries involved with those even and odd functions. And then we're going to be talking about piecewise functions, right? So let's go ahead and list those ideas, right? Okay, so I wrote down the topics, right? Again, increasing and decreasing parts of functions, relative max and mins, high points, low. That means the high points and low points on the graph. If a function is even or odd, right? And what kind of symmetries it has, and understanding and using piecewise functions. Okay. Let's go and start with the first part, increasing and decreasing parts of a function, right? So if we had some sort of graph of a function, right? Okay, so I drew a little kind of a graph here. And I labeled this point A here, and I labeled this point B here. That's going to be kind of a high point and a low point that we kind of talked about a little bit, right? As you can see here on the left of A, this function is kind of going upward. Again, that's increasing. After A, it kind of goes downward, and then kind of at B and after B, it goes back upward, right? So A and B are going to be our relative max and mins. Again, relative max being the high point, relative min being the low point. And between these relative points, relative max, relative mins, the function is either increasing or decreasing, right? So on the left, again, increasing, you just follow this graph left to right and just look at the motion of the graph and kind of see how it's moving. So on a graph, it's kind of easy to tell how these functions are moving as far as increasing and decreasing. How do we see that as far as some sort of other function, right? Let's say we had some sort of function let's say we had the function f of x equals, let's say, x squared plus 2, right? We could always draw this graph and see exactly how this function is increasing or decreasing, right? Or we can say, is it increasing at a certain point, right? So let's say we drew the graph of this x squared plus 2, okay? So the graph of this x squared plus 2, go ahead and draw it here. It's kind of like this, okay? And so we notice that here at that intercept, this function is kind of decreasing before it on the left and then increasing after it on the right. If we follow this left to right, we see that it's decreasing here and then increasing up after this low point. And that low point, again, is going to be a relative min, right? Okay. So now if I asked you, is the function increasing at a certain point, right? So is f of x increasing at some x being 2, right? So we can look at the graph. Again, 2, you would have some y value of 4, and then before it, right, you can think about what happens at 1. What happens kind of really close to 2 on the left? What happens kind of really close to 2 on the right? And you can plug values in and see that, okay, well, before x being 2, the y value is smaller. After x being 2, the y value is bigger, right? So you can say something like this, right? F at 1, that's going to give me, of course, 1 squared plus 2. And it gives me 3. Right? The function at 2, right? I wind up with 6. And the function at 3, I wind up with 11. We notice that as we move larger and larger in the x direction, this function winds up getting larger and larger in the y direction, again, after 0, right? As we saw in the graph. So even if we don't have the graph, we can still kind of plug in numbers and see the direction that this graph is going, right? And again, you have more accuracy in this prediction of the motion of the graph if you have tighter and tighter numbers closer together, maybe like a 2.1, 2.2, 2.3, things that are really close, right? Again, I'm using 1 and 3 because, you know, I know exactly how this graph is going to behave. And if it's a very nice function like quadratic or any sort of polynomial, we can kind of gauge it in that sense as well. Okay. So we went ahead and talked about relative max, relative mins, increasing and decreasing pretty thoroughly here. So let's go ahead and move on to our next topic, and that is to talk about the even and odd property of a function. And sometimes it can either be even or odd, right? And then what kind of symmetries this will have. Okay. All right. So let's talk about a function being even, right? Again, a function is going to be even if it satisfies the equation the original function is equal to the function with the negative version of that x value plugged in for any x in the domain. Okay. Cool. That's what it means to be an even function. If a function does not satisfy this equation, then it's not an even function. Okay. And just because the function is not even does not make it odd. Again, we're going to talk about a function being odd now. Again, it's going to satisfy an equation as well, just like this one did. I didn't put it. It satisfies the equation. Here again, the original function f of x will be equal to the function with a negative x plugged in, and then you multiply it with another negative 1 in front. Okay? Again, for any x in the domain. Okay? So it has to satisfy one of these equations. Either it's even when we have the original function equal to if we plugged in a negative x, or it's going to be odd if the original function is equal to the one above, again, f with a negative x plugged in, but then you multiply with a negative 1 again on the outside. Okay? And if it doesn't satisfy any of these equations, then we say that the function is not even and it's not odd. Okay? Pretty straightforward. Either it's one or the other or another. No, neither, sorry. Okay? So let's go ahead and start the talk about the symmetries, right? So if a function is even, it's going to have symmetries kind of mirroring over the y-axis. I'm going to go ahead and show with a graph what that means. And we actually have an example of an even function above. This function we just used, x squared plus 2. Okay. We had already drawn out that function. And we see that regardless of which side we're on, like let's say I choose a 1 as my input, right? X being 1, then I'll get a 3 as an output because I'll be plugging in that 1 into x squared or 1 squared is 1 plus 2 is 3. If I plug in a negative 1, I'm going to wind up with negative 1 squared, which is positive 1, plus 2 is 3. So you see I get 3 on each side as a y output, so it has that symmetry. The y values are the same whether I have the positive version of the number 1 or the negative version of the number negative 1. The same thing with 2 and 3 and 4, right? With their counterparts, right? Negative 2, negative 3, so on and so forth. And you can actually do it in general. Let's check if it's even, right? Well, we can say, all right, let's go ahead and plug in a negative x instead of just regular x. So if I have f of x being x squared plus 2, if I plug in a negative x and I replace that x with a negative x. And when I square that negative x, again, the negative times negative turns positive. So I wind up with a positive x squared plus 2, which is the exact same function that we started with. And that's what it means when I say f of x equals f with a negative x plugged in. You actually plug in a negative x, see what the function does to that negative x, and see what the result is. And if the result happens to be f of x, then we're in business. It's an even function. And again, these functions will either be even or odd or neither. They're never going to be two at the same time or more than one at the same time. So because we show that this was even, it will not be odd. And we can actually show it's not going to be odd, right? By checking it, right? When we looked at the odd, what it meant to be odd, we had that the original function was the same as if I had plugged in that negative x and then multiplied it with a negative 1 on the outside. So we already know what this part f with negative x is. We actually just computed that above. F of negative x wind up giving us x squared plus 2. Right? We had just finished figuring that out. So we know that this is now going to be a negative 1 times f of negative x, which is x squared plus 2. And we wind up seeing that this is negative x squared minus 2 after we distribute that negative 1. And that's not the original function. The original function was positive x squared plus 2. So that's how we can say that it's not even. or not odd, sorry, not odd. So this function is not odd. All right. So let's talk about the symmetries on an odd function, and then testing to see if a function is odd, which we already kind of did that. Okay. So an odd function has symmetries about the origin. Okay. And what this means, symmetries about the origin, it means that it actually has symmetries across both axes, right? Or you would say across this line y equals x is an easier way of saying that as well. Okay. So what that means, let's go ahead and have an example of an odd function. A cubic function is a perfect example of an odd function. Okay. So here's the origin right here at 0, 0. Okay. I'm going to kind of highlight and maybe that'll, when I highlight, maybe that'll give you a better idea and keep track of where those symmetries are. Here's an orange here. Okay. So let's say I flipped over the x-axis, right? And if I flipped over the x-axis, it'll look something like this, right? And again, the orange will be on this side now, and the yellow will be on this side now. And then what would happen if I flip over the y-axis now? Or sorry, this one was the y-axis, sorry. The first one was y-axis, and the second one's going to be x-axis. And it doesn't matter which order you do it in. You could have done the x-axis first and y-axis after. Okay. So I flip this over the y-axis. This orange bit on the left is going to go underneath. And I just realized that the orange looks very similar to the yellow on my screen. So let me change that to like a red. Yeah, that looks good. Okay. Let me go ahead and flip the thing over the x-axis, and this red part on the left will come underneath now. Right? And then this yellow part will kind of just come up. Right? And it's going to look exactly the same as the original that we had. Again, minus me not having good artistic skills, but if this was drawn with precision, you would see that it's the exact same thing. So odd functions behave in this way. They have these kind of symmetries. We say it's symmetric over the origin. It's symmetric over 0, 0, but it's the same as saying it has symmetry over both axes. And you can do them in steps. Okay. All right. So we had just done checking if something is odd. Let's give an example of one that actually is odd, show that it is odd, and then also show that it's not even. Okay? So let's say we have another function, g of x is equal to x cubed plus 2x. Okay. So let's show that this is odd. And also that it's not even. Okay. So to check if it's odd, we're going to multiply this g with a negative x plugged in times a negative 1. Okay. So I'm going to have that negative on the outside, and let's write out what g of x, right? What g of x with this negative x plugged in looks like. So we take this g of x, and I plug in a negative x everywhere I see x originally. Okay? And again, all of this is g of x, so I have to wrap that up in parentheses, because that negative in front of g of x, or g of negative x, belongs to that entire thing. Okay, so I need to figure out what this inside part is first, and then distribute that negative afterwards. Okay, so negative x cubed. So it's a negative times a negative times a negative, which makes it positive. Sorry, a negative, which makes it negative. Sorry, negative times negative is positive, and then an extra negative makes it negative. And then this is 2 times a negative x, positive 2 times negative x, which is negative 2x. Okay. So I go ahead and multiply this negative in. That turns that negative x cubed positive, and also turns this 2x positive as well. And again, this is the original function we started with. So this thing is odd. Okay. Again, let's show that it's not even. If I just did this negative x part, that would be the same as that first bit that I just did without distributing that negative. And we see that this is not the original function, because the original function had positive x cubed and a positive 2x. So it's not even. All right. Hopefully this kind of gives you insight as to even and odd functions, why they can only be one or the other. And again, if you have questions, go ahead and email me. We can set up a one-on-one little interview like this, or a meeting, I should say, so that way I can show you maybe with detail, just like I'm doing here with the notes. Okay, let's have an example of one that's not even or odd at all. And you're going to notice that it's going to have a mixture of something that looks even and something that looks odd. Okay. All right. So let's check if it's even. Let's check if it's odd. And let's have the directions say, show that h of x is not even and not odd. All right. So again, let's check even first by plugging a negative x in. So we're going to have a negative x being cubed plus a 2 times a negative x being squared plus a negative x, right? And we see that that's going to give us a negative x cubed plus 2x, because negative x, 2x, sorry, positive 2x squared, because a negative x squared is positive x squared, minus another x at the end. Okay. This is not the original function because we see that this x cubed is a negative in front of it, and this x at the very end also has a negative in front of it. Okay. And again, if you've been kind of seeing a pattern here, after we test that something is even, we can use that information to test if it's odd. Because when we test if it's odd, and again, we can put that here, right? Let's move this a little bit. So testing for even was right there, testing for odd. Again, we're going to be looking at negative h with a negative x plugged in. And again, we already know what this first part, h of negative x, is. We just did it right before. So we know that that's going to be a negative x cubed plus 2x squared minus x. And that's why I like doing even first, then odd, because you're going to be using the even computation that you did in the odd computation testing. Okay, so we just distribute that negative, and we get an x cubed minus a 2x squared plus an x. And we see also this is not the original function because that 2x squared part in the middle is not positive. It's actually negative, and the original had it positive in the middle. Okay. So again, we say that h of x is not even and not odd. And other choices, like answer choices, you would say that it's neither, right? So h of x is neither. And again, you would just use the answer choice neither. If it's like a multiple choice, it'll just say neither. Or if it's a free response, you would also just put neither, kind of just to speed up the process a bit. If you want to write it, h of x is neither even nor odd, that's perfect. Okay. Let's move on to our last topic then. So our last topic for this section is going to be piecewise functions. And let's talk about piecewise functions. I like to tell people that it's kind of like a Frankenstein function, right? You take a bunch of functions that we already know, and you take parts of them, and you kind of glue them together, or you put them together on the same graph, but only parts of the functions. So it'll have one part of the function being this, and another part of the function being something different. And it'll look kind of weird, but once you can understand by reading what the function is telling you to do, it's very easy to get accustomed to. Okay? And when we talk about the pieces of the function, they're going to be over certain domains. So over certain x values, the function will behave a certain way. And then over other x values, it may behave differently. Okay? So let's talk about piecewise functions. Okay. Let's look at the look, right? The notation of a piecewise function. And then we'll be looking at many piecewise functions and how they look. So when we look at a piecewise function, it's going to have the same standard, notation, whatever you want to call the function, f or g or cat, or whatever the name of the function is. And then you're going to have this curly brace here, at this bracket. And then you're going to have a bunch of functions here. Let's say I have one function like this. Let's say I have another function like this. Let's say I have another function like this. Okay. And then you're going to have domains for each of those functions. Let's say here, the first function x plus 1, this f of x behaves that way. Let's say for all the x's that are less than negative 1. And then this x squared plus 2x, let's say that it behaves that way at exactly negative 1. And then everything up until, let's say, 2, not including the 2 for that one. And let's say the last part, the negative x plus 5, let's say this function behaves that way from 2 onward. Okay? And so these less than or equal to's are going to be very important because remember what it means to be a function. There should not be more than one output for any input. So these x values, these domain values for x are going to be inputs. So if I had the or equals on more than one of these overlapping values, then there would be two y values there because I'm able to look at one of these functions, say here the middle one. I will be able to plug in 2 for that one and then also be able to plug in 2 for the third part. And that would give me two different y values possibly. It might not. Sometimes you have overlap where it's okay, but for the majority of the time, there are going to be cases where these things have a very big jump. They're disconnected. And if you had more than one y value for those disconnected parts, then it would no longer be a function. The vertical line test would say, oh, the definition of it being a function would no longer work. Okay. Right then. Let's go ahead and draw out this function. I'm not going to draw it by hand because I think there's more value in me posting an image or sharing a screen for having that. So let me go ahead and pause the video real quick and pull that up. Okay, and we're back. So let's go ahead and, how do I do this for the Apple? Here we go. So here is the function. Again, it's going to look weird on Desmos on how I have to type it in, but this is what the function will look like. And as you notice on the left here, this is going to be that function x plus 1. Okay, and it's going to behave that way all the way before x being 1. Okay? So this does not do a very good job on showing the parts where it should have open and close things. Here you will have a solid dot at -1, 0, and you will not have a solid dot up here. You see how I'm actually able to click on it here, but there's no solid dot on this right side for the x squared. Again, and that comes back to, okay, why did it just go away? That comes back to having this not or equals. So let me go ahead and change that. I think I put it in wrong. Let's change that. I put the or equals there. So this one should be not or equals. Perfect. There we go. So there's no, well, it shouldn't be there. So because there's no or equals, this should not have a solid dot there. The solid dot should actually be up here. Why this is behaving that way, again, this program is not what I had in mind. Oh, please no. When I was trying to create this image. I'm not proficient with apples, so I don't know how to zoom back out now. Awesome. Maybe in the future I'll figure that out. But again, you will see solid dot up here at -1, 3. You will see an open circle here. You'll see an open circle here. And then you'll see a solid dot up here at 2, 3. Okay. So if I did draw that back on, here again as a rough sketch, you would have that original line there with an open circle, and then you have this quadratic here with a solid dot here, coming down. Oops, I'm shaking so much. Like that. It will have an open circle here. And then this last bit at 2. I have a solid dot there, coming down. This part's not right. And something like that. Again, just a sketch, not something amazingly accurate. Okay. They don't have those open circles to exaggerate that it's not there, and those closed circles to exaggerate that it is there. Okay. Right then. So that's how we're going to understand piecewise functions. Now we're going to be using piecewise functions. We'll be plugging into these piecewise functions. So let's take this example and go ahead and plug in some values. Let's say I have this f of x function. Let's go to compute. F with, say, -2 plugged in. F with, let's say, 0 plugged in. F with, let's say, 4 plugged in. And then talk about what parts of the function they need to be plugged into. So when I plug in -2, we notice that -2, that first domain is where it exists, right here, right? It is -2. And then if I look at 0, 0 exists in that second domain. And then if I look at 4 exists in that third domain because it's after 2. So I picked 2 points that were specifically in each part of those domains. So when I plugged them in, I plugged them into that function that it belongs to, the domain where that function belongs. So for f of -2, since it belongs to the first domain, right, I go ahead and plug that into the x plus 1 part. And again, we wind up with -1. When I plug this into, when I plug 0 into this function, that belongs to the middle domain. Again, it's between -1 and 2 as an x value. So I plug it in there. I wind up with 0. When I plug in a 4, again, it belongs to that last part of the domain. So I plug it into that last function. I wind up with a 1. And if we were going to draw this function and actually plot points and sketch it, this is how you would do it. You would actually plug in points and then draw the dots on your graph and then sketch out this graph. Okay. So hopefully this is useful for you all. Again, give me feedback on these videos. Again, if you have any questions about the topics, or you need me to go more in depth, go ahead and email me. I can set up a video conference so we can do more one-on-one things. And have a good day, y'all. More to come soon.